You know what is fascinating right now? As you are sitting there listening to me, the atoms in your body are doing things that make absolutely no sense. I don't mean they're behaving in complicated ways that you need years of study to understand. I mean they're doing things that genuinely violate everything your common sense tells you should be possible. And I spent decades trying to explain these impossibilities to people, not because I fully understood them myself. I was very clear about that. I always said, and I'll say it again, I think I can safely say that nobody understands quantum mechanics. But I could explain what we observe, what we measure, what actually happens when we do experiments. And what actually happens is completely insane. Let me start with the most famous mystery, the one that has been haunting physics since the early 1900s. It is called wave-particle duality, and it shows up most dramatically in something called the double-slit experiment. Now, this experiment is beautifully simple. You could almost do it in your garage if you had the right equipment. But the implications, the meaning of what happens, physicists are still arguing about that today. Here is how it works. You take a barrier, just a simple wall, and you cut two narrow slits in it, two parallel openings. Then you fire particles at it. Could be electrons, could be photons of light. Doesn't really matter. You fire them one at a time at these two slits, and you watch where they land on a screen behind the barrier. Now, what should happen, common sense, says each particle goes through one slit or the other. Right? It is a tiny chunk of matter. It is a particle. It has to pick a path. And if you close one slit and just leave the other open, that is exactly what you see. You get a simple pattern on the screen. A bright band right behind the open slit. Makes perfect sense. Particle goes through the hole, hits the screen. But when you open both slits, something impossible happens. You don't get two bands. You get multiple bands. An interference pattern. Light and dark stripes spread across the screen. And that pattern, that specific arrangement of bright and dark regions, that is the signature of waves interfering with each other. When waves overlap, they can add together to make bigger waves, constructive interference. Or they can cancel each other out, destructive interference. Light waves do this. Sound waves do this. Water waves do this. But particles, how in the world does one particle interfere with itself? See, that is the thing that should break your brain. You are firing particles one at a time. There is only one particle in the whole apparatus at any given moment. It is not like they're bumping into each other or communicating somehow. Each individual particle goes through both slits at once, interferes with itself like a wave, and creates this wave pattern. That is not poetry. That is not a metaphor. That is what the mathematics says is actually happening. The particle exists in what we call a superposition, simultaneously taking both paths, and only when it hits the screen, only at that moment, does it suddenly become localized at one specific spot. But here is where it gets even stranger. And this is the part that really gets people. If you try to observe which slit the particle goes through, if you put a detector there to watch what is happening, the interference pattern vanishes, completely disappears. The particles start behaving like normal particles again, going through one slit or the other, creating just two bands on the screen. The act of measurement, the act of observing, fundamentally changes what the particle does. And it is not that you are disturbing it with clumsy equipment. People thought that at first maybe the detector bumps the particle, changes its path. Number it is deeper than that. Before measurement, the particle genuinely exists in multiple states at once. After measurement, it doesn't. The universe seems to care whether you are watching or not. I love talking about this because it illustrated something I thought was absolutely crucial to understanding quantum mechanics. Nature doesn't care what makes sense to you. Nature doesn't care about your intuition, your common sense, your deeply held beliefs about how reality should work. The universe operates by rules that are completely alien to human experience, and you just have to accept that and deal with it. Don't ask how it can be like that. Don't demand an explanation that fits your everyday experience. Just accept that it is like that and learn the rules. The rules work. They predict experimental results with incredible precision. That is what matters. Which brings me to the second mystery, superposition itself. Now, I just mentioned superposition when talking about the double slit, but it deserves its own discussion because it is so fundamentally weird. In classical physics, in the normal everyday world you experience, things have definite properties at every moment. This cup is here, not there. This coin shows heads or tails, not both. Everything has a specific state. But in quantum mechanics, particles can exist in multiple states simultaneously until you measure them. An electron can be spinning up and spinning down at the same time. A photon can be polarized vertically and horizontally at the same time. And it is not that we don't know which state it is in and we're just ignorant. It is genuinely in both states. The most famous illustration of this is Scharfeidinger's cat. You've probably heard of it. You put a cat in a box with some device that might or might not kill the cat based on a quantum event, maybe a radioactive atom, that might or might not decay. According to quantum mechanics, until you open the box and look, the cat is both alive and dead simultaneously. Now, Scharfeidinger proposed this as a criticism, as a way to show how absurd quantum mechanics seemed when you tried to apply it to everyday objects. He thought he was making fun of the theory, but the joke's on him because quantum mechanics is actually correct. The mathematics works perfectly. It predicts experimental results with stunning accuracy. The problem is that superposition doesn't obviously scale up to big objects like cats. Cats are made of something like 10 to the 27th atoms, an astronomical number, and all those quantum states get tangled up with the environment incredibly quickly in a process we call decoherence. The superposition gets destroyed so fast that we never see macroscopic objects in multiple states at once. But for individual particles, for atoms, for small molecules, superposition is absolutely real. You can trap ions in superpositions that last for seconds. You can create what we now call quantum computers that exploit superposition to perform certain calculations that would be completely impossible for classical computers. I understood this, I think, better than most people at the time. I realized that superposition wasn't a bug in our theories, wasn't something we needed to fix or explain away. It was a fundamental feature of reality, and I developed a whole mathematical framework, the path integral formulation, to describe it properly. Which actually, that is our fifth mystery. But I am getting ahead of myself. Let me tell you about number 3. First, entanglement. Entanglement is what Einstein called spooky action at a distance. And he meant that, as an insult, Einstein hated this aspect of quantum mechanics with a passion. He thought it proved the theory was incomplete, that there had to be some deeper explanation we were missing, some hidden variables that would restore sensibility to physics. But he was wrong. I hate to say it, because Einstein was a genius, one of the greatest physicists who ever lived. But on this point, he was wrong. Entanglement is real. It has been experimentally verified thousands of times, and it is arguably the weirdest thing in all of physics. Here's how it works. You can create two particles in such a way that their properties are correlated, connected. Maybe you create two photons from a single source, or you split one particle into two pieces. These particles become entangled, linked in a way that has absolutely no classical analog, no comparison in everyday experience. Now, if you measure one particle and find it has a certain property, let's say you measure its spin and find it is spinning up, then instantly, immediately, faster than you can blink, the other particle will be found spinning down. No matter how far apart they are, not after a signal travels between them, not after information propagates at the speed of light, instantly, immediately. You can separate these particles by miles, by light years even, and the correlation persists. Measure one, and you instantly know something definite about the other. And it is not that they secretly agreed on their states when they were created, like they're following some predetermined script. Experiments have ruled it out conclusively through what we call Bell's inequality tests. John Bell proved mathematically that no local hidden variable theory could reproduce the predictions of quantum mechanics. And experiments confirmed quantum mechanics was right. The particles genuinely don't have definite states until you measure them, and yet their random outcomes are perfectly correlated across arbitrary distances. The universe somehow maintains this connection instantaneously. Now, you can't use this to send information faster than light, and that is important. The results you see when you measure your particle are completely random. You can't control them, can't encode a message in them. So you can't violate relativity, can't send signals faster than light. But the correlation is there, undeniable, unexplainable, by classical physics. It is like the universe has some kind of underlying connection, some layer of reality that doesn't care about space and distance the way we normally think about them. This leads directly to mystery. Number 4, probability amplitudes. Now, this is where the mathematics gets really interesting, and it is something I spent a lot of time thinking about and teaching. In classical probability, you have a probability for each outcome, a number between 0 and 1, and you add probabilities for different ways something can happen. Simple, straightforward. Makes sense. But quantum mechanics doesn't work with probabilities. It works with probability amplitudes. These are complex numbers. Numbers that have both a magnitude and a phase, like a wave has an amplitude and a phase. And the rules for combining them are completely different. When a particle can take multiple paths to the same final state, you don't add the probabilities of each path. You add the amplitudes, these complex numbers, and then, only then, you take the absolute square of the total amplitude to get the actual probability. This is why you get interference. The amplitudes can add constructively or destructively. They can cancel each other out completely. Probabilities can't do that. Probabilities are always positive. They can only add up, never subtract. But amplitudes can cancel. And that is why you see interference patterns in the double-slit experiment. The amplitude for going through one slit and the amplitude for going through the other slit can cancel each other out at certain points on the screen, creating dark bands where particles never land. This isn't just mathematical trickery. This is how nature actually works. And once you accept this, once you understand that nature computes with these probability amplitudes rather than probabilities, a lot of quantum mechanics starts to make more sense. Not intuitive sense, it'll never be intuitive, but mathematical sense. The equations become clear, the predictions become precise. Which brings me to mystery number 5, path integrals. This is my formulation of quantum mechanics, and I am quite proud of it. The idea is beautifully simple, but profoundly strange. In classical physics, a particle moving from point A to point B takes one definite path. The path that minimizes something called the action. That is the principle of least action, and it has been known for centuries. But in quantum mechanics, I realized the particle takes every possible path simultaneously. Every single path from A to B, no matter how crazy, how twisted, how impossible it seems, contributes to the amplitude. You calculate an amplitude for each path, and then you add them all up, integrate over all possible paths, hence path integral. Paths that are close to the classical path tend to add up constructively because their phases are similar. Paths that are far from the classical path tend to cancel out because their phases vary wildly. And in the limit where quantum effects are small, where Planck's constant is effectively 0, all the weird paths cancel out, and you are left with just the classical path. That is why big objects seem to follow classical mechanics. All the quantum weirdness averages out. But for small particles, for electrons and photons, all those paths matter. The particle genuinely explores every possible route through space and time. It goes around obstacles both ways at once. It takes straight paths and curved paths and loopy paths, all of them, simultaneously. And only when it arrives at the destination do all these amplitudes combine to give you a probability of finding it there. This sounds insane, I know, but it works. It gives you the same predictions as standard quantum mechanics, and in many situations it is actually easier to calculate with. Plus, it gives you this beautiful picture of particles exploring all possibilities at once. Now, mystery number 6, the uncertainty principle. Heisenberg came up with this in 1927. And it is one of the most profound statements about reality ever made. It says you cannot know both the position and momentum of a particle at the same time with perfect precision. The more precisely you pin down the position, the more uncertain the momentum becomes. And vice versa, the more precisely you know the momentum, the more spread out the position becomes. This isn't about measurement error. This isn't about clumsy equipment disturbing the particle. This is fundamental. The particle literally does not have a definite position and a definite momentum at the same time. Think about what that means. In classical physics, a particle has a position, and a velocity at every instant. You can, in principle, know exactly where it is and exactly how fast it is moving. That is determinism. That is predictability. But quantum mechanics says no. That is not how reality works. You can't specify both. If you confine a particle to a small region of space, it has to have uncertain, large momentum. That is why electrons don't fall into the nucleus, which I explained in my lectures on atoms. The smaller the region you confine them to, the more they jiggle around, the more momentum uncertainty they have, and that motion, that kinetic energy, keeps them from collapsing. This principle shows up everywhere in quantum mechanics. It is not just position and momentum. There are other pairs of quantities that can't be simultaneously known with perfect precision. Energy and time form another pair. The longer you have to measure something, the more precisely you can determine its energy. Try to measure energy in a very short time, and the uncertainty becomes large. This affects everything from atomic spectra to the decay of particles to the behavior of fields. The uncertainty principle is woven into the fabric of reality. And finally, mystery number 7, the measurement problem. This is the big one, the one that people still argue about, the one that probably has philosophers debating more than physicists at this point. The question is simple. What happens when you measure a quantum system before measurement? The system is in a superposition of multiple states. After measurement, it is in one definite state. How does it go from one to the other? What causes the collapse of the wave function? The mathematics of quantum mechanics tells you how to calculate probabilities for different measurement outcomes. But it doesn't tell you what physically happens during measurement. Does the wave function really collapse? Is collapse a physical process or just an update of our knowledge? Does it happen instantaneously? What counts as a measurement anyway? Does it require a conscious observer, or does any interaction with a large classical system count? I never pretended to have answers to these questions. I would tell my students, look, I can tell you how to calculate. I can show you the equations. I can predict what you'll see in experiments with incredible accuracy. But what is really happening, what reality is doing behind the scenes, I don't know. Nobody knows. And maybe that is okay. Maybe that is not even the right question to ask. Physics is about predicting the results of experiments, and quantum mechanics does that perfectly. Whether there is some deeper reality underlying it, some mechanism we haven't discovered yet, that is philosophy as much as physics. What I can tell you is this: the wave function, this mathematical object that describes the quantum state, evolves smoothly and deterministically according to Schur-Feidinger's equation when you are not measuring it. Everything is predictable. Everything follows rules. But when you make a measurement, something different happens. The wave function collapses to one of the possible outcomes randomly, with probabilities given by the Born rule, and we can't predict which outcome you'll get for any individual measurement. We can only predict probabilities. That randomness, that fundamental unpredictability, is built into nature at the deepest level. Einstein hated this. He famously said God does not play dice with the universe. But as far as we can tell, that is exactly what happens. The universe does play dice. Individual quantum events are genuinely random. You can't predict them, even in principle, even if you knew everything there is to know about the system. All you can predict is probabilities. And experiments have confirmed this again and again. There are no hidden variables, no secret information that would let you predict individual outcomes. The randomness is real. So those are the 7 mysteries: wave-particle, duality, superposition, entanglement, probability, amplitudes, path integrals, the uncertainty principle, the measurement problem. Each one of these defies common sense in a different way. Each one forces you to abandon some deeply held belief about how reality should work. And together, they paint a picture of a universe that is far stranger than anything we could have imagined. The thing is, despite all this weirdness, quantum mechanics works. It works spectacularly well. It is the most accurate theory in the history of science. Some predictions of quantum electrodynamics, the theory I helped develop, match experiments to something like 10 decimal places. That is extraordinary precision. So even though we don't understand it in the intuitive sense, even though it violates common sense at every turn, we know it is correct. Nature really does work this way. I spent much of my career trying to make quantum mechanics accessible, trying to explain it to students and the public without watering it down too much, because I think it is important for people to know that the universe is weirder than they think. More subtle, more beautiful in its strangeness than the simple mechanical picture we inherited from Newton and classical physics. The world isn't made of little billiard balls bouncing off each other. It is made of quantum fields and probability amplitudes and particles that take all paths at once. And here is what really gets me. All of this, all these bizarre quantum effects, they're not just theoretical curiosities. They're real. They're happening right now in every atom of your body. The electrons in your cells are in superpositions. The photons hitting your eyes are exhibiting wave-particle duality. The particles in your brain are subject to the uncertainty principle. You are a quantum mechanical system through and through. It is just that you are so big, made of so many particles, that all the quantum weirdness averages out and you appear classical. But sometimes quantum effects do show up at the macroscopic scale. Superconductivity is purely quantum mechanical. A superconductor is basically one giant quantum state with billions of electrons all acting together coherently. Lasers are quantum mechanical. The light in a laser is in a special quantum state where all the photons are perfectly synchronized. Even DNA, the molecule that carries your genetic information, relies on quantum tunneling for certain mutations. Quantum mechanics isn't just about tiny particles in laboratories. It is the foundation of everything. What I always tried to emphasize in my lectures was that you shouldn't be frustrated by not understanding quantum mechanics intuitively. I don't understand it intuitively either. Nobody does. Our brains evolved to deal with rocks and trees and animals, things on human scales moving at human speeds. We have no intuition for what happens at atomic scales, for objects that act like waves and particles simultaneously, for probabilities that can be negative. There is no reason we should have that intuition. We've never encountered these things in everyday life until recently. But we can understand the mathematics. We can learn the rules, we can make predictions and test them. And that is what science is really about. Not finding comfortable explanations that make sense to your everyday intuition, but finding accurate descriptions of how nature actually behaves. And if nature behaves in ways that seem impossible, well, that is nature's problem, not ours. Or rather, it is our problem to accept it and adapt our thinking, not nature's problem to conform to our expectations. The 7 mysteries I've described, they're not going away. They're fundamental features of reality, as far as we know. Maybe someday someone will come up with a deeper theory that explains quantum mechanics in terms of something even more fundamental. People have tried. There are interpretations like pilot wave theory, many worlds interpretation, objective collapse theories. Each one tries to make sense of quantum mechanics in different ways. But none of them change the predictions. None of them make quantum mechanics less weird at its core. They just redistribute the weirdness to different places. So what do we do with all this? How do we live in a quantum mechanical universe? Well, mostly we ignore it because at human scales the classical approximation works just fine. You don't need to worry about superposition when you are driving your car or making dinner. But in technology, we're increasingly using quantum effects deliberately. Quantum computers are being built. Quantum cryptography is becoming real. Quantum sensors are achieving unprecedented precision. We're learning to harness the weirdness to make it work for us, rather than just being puzzled by it. And scientifically, these mysteries continue to drive research. People are still trying to understand the measurement problem, still exploring the limits of entanglement, still developing better ways to formulate and teach quantum mechanics. Every generation of physicists wrestles with these questions. Some make progress, some just get confused in new and interesting ways. But the conversation continues because the mysteries are so deep, so fundamental, that we can't help but keep thinking about them. You know what I find most beautiful about all this? The fact that the universe can surprise us. That reality doesn't have to make sense to us. That there are depths to nature we're still discovering, laws we're still uncovering. We thought we had physics mostly figured out at the end of the 1800s. Then quantum mechanics came along and showed us we didn't understand anything at the fundamental level. And now, more than 100 years later, we have the theory. We can use it. We can make incredibly precise predictions, but we still can't claim to truly understand it in the way we understand. Say, why balls roll downhill. That is okay. That is exciting. That means there's still mystery left in the world, still things to figure out, still ways in which the universe can surprise us and challenge our thinking and force us to expand our conception of what is possible. These 7 quantum mysteries aren't problems to be solved and then forgotten. They're windows into the deep structure of reality, and looking through them, we see a universe far stranger and more wonderful than we ever imagined.